Hey everybody, and welcome back to Algebra 2 Online. So this video is going to be just another one on some double angle identities, solving some trig equations, using identities and things like that. To start off though, I just want to do another one of these verify a trig identity, and when I typed this problem in, I accidentally typed the wrong thing, which is why I've kind of had to wipe this out. But anyway, so anytime you're verifying identities, you always want to take the more complicated thing and simplify down to the easier thing, right? And anytime you have two different fractions, it's good to get a common denominator because this is one thing, right? So we'll probably have to combine this into one thing. So easy common denominator here would just be 1 minus cos times 1 plus cos, because, you know, a common denominator is always just the two, denominators. So we will just multiply the left one by 1 plus cosine. And so we'll get that on top. And then we'll multiply the other one. Sorry, I'm just thinking and writing. We'll multiply the other one here by 1 minus cosine on top and bottom. And then you can combine them, right? And, you know, on the top, you'll have 1 plus 1 is 2. Cosine minus a cosine is 0, right? And so we'll literally just have a 2 on top. And then when we multiply out the denominator, right, we multiply this. You know, this is the common denominator. So we're just going to multiply that out. We're going to get 1. It's a difference of squares, really. So you'll get 1 minus cos plus cos. 1 plus cos minus cos, and then you'll get a minus cos squared. So 1 minus cos squared, theta. And then this is where we can use a trig identity. So we just use the Pythagorean trig identity. 1 minus cosine squared is sine squared. And then, of course, 2 over sine squared is going to be 2 cosecant squared. And so that's it. So you've taken the complicated thing and you're just doing, some basic kind of trig algebra stuff to get down to the simpler thing. So really what we do with these things is, again, we take these kind of crazy looking things sometimes and we want to simplify it and get an easier equation to solve, right? Trying to think about what theta is here on top and bottom in this form is hard, but we can, we might be able to simplify it and solve it that way. So I'm going to start by just doing like some trig identity stuff. So tangent squared, you're not going to really do much with that. Tangent squared plus 1, though, is, right over here. It's equal to secant squared. And so I can do secant squared there. And then if I do this in terms of sines and cosines, I have sine squared over cosine squared, all over 1 over cosine squared, right? And so the cosine squareds are going to cancel, and you're going to have just sine squared. And so now, basically, this whole thing is simplifying to just sine squared theta, and that's set equal to 3/4. And so, just unpacking the square, you're going to have sine of theta then equals plus or minus root 3 over 2. And now there is, a nice problem that we can solve here. So this is where we can just use like the finger trick kind of backwards. And I'm going to introduce a new term here. So I'm going to actually say, instead of finding all angles that make this trig equation true, because there would be infinitely many, of course, for those. You can just keep going around the circle. I'm actually going to change it and just say find, this is something that you'll see a lot of times in trig stuff. You're just going to find the principal, I think it's that principal, yes, principal root. So what I mean by this is really just the first solution you get in the circle, okay? So instead of basically going around and around and around, sometimes we just need to know the first time that we get these answers here. And so if we just kind of draw our circle, right, we're thinking all students take calc. The first time you're going to get the positive root 3 over 2 is certainly in the first quadrant. So we're going to have some triangle there. And then, that's be what we're solving for in that one. And then the first time you'll get a negative is not here, but down in here. So we're going to have another triangle problem to kind of think of here. I guess really that's the angle. And then you basically just use the finger trick thing. Sine is square root of fingers below. And so, you've got a root 3, so you got 3 fingers below. So this angle in here has to be like a 60 or pi over 3. So theta is, let's say, pi over 3. So that would be the principal root for the positive one. And then the negative one, this angle in here is still like a pi over 3. And this, to this point, is 3 pi over 3. So we go one more. So it's 4 pi over 3. So 4 pi over 3 for that other one. So that's what we would call the principal roots for this problem. One other thing, I want to say too, when we're solving these equations, we still have like a rational function here. We have, variables on top and bottom. So you should always do your domain check stuff. You need to know that what your answers are not going to give you something undefined. And, you can see that if you just plug in pi over 3 and 4 pi over 3, you won't get 0, because the only time, you're going to get 0 on the bottom is if this is -1, if this is -1, but it's squared, and so it can't be -1. So it's good to check your answers and just make sure that they work, but here this thing is always going to be positive on the bottom. It's non-zero on the bottom, I guess. So that's what we would call finding the principal root of for this equation. If you wanted to do all of them, right, you would have technically an answer in every quadrant, because there would be 2 that are positive and there'd be 2 that are negative. And then again, you can go around and around and around and around and around. But that is how we would do it for a principal root case. All right. So I just want to do another trig equation here. And I want to kind of do, show you with this u sub thing again. So, this is a quadratic sine trig equation. And since it has quadratic structure, we can do this trick where we're going to let u equal sine of theta. So then 2u squared plus u is actually equal to 0, right? And then it's one of these things where you can just factor the quadratic, and now you can just think about it as a quadratic. So you're getting either u equals 0 or u equal -1/2, right? And so for this one, now if we just unsubstitute, sine of theta equals 0, right? And we are asked for just solutions in the first lap on the circle, right? So if we just think, first circle, here's a circle. When in that first lap do we get sine equals 0? Well, that's just where the y value is, equal to 0, and that's just right here on the x-axis. So y value equals 0 at 0, and then at pi. So the solutions on that one are 0 and pi. And then for this one, right, sine of theta needs to equal -1/2, right? And so in that one, we have to think a little bit more about it, because, we're actually going to have to do some kind of triangle stuff. We're not in this quadrant or this quadrant because it's positive. And so, you've got some sort of triangle here and some sort of triangle here. And basically it's just finger trick stuff. You want to do square root of fingers below and get 1. And so the reference angle has to be a 30. It's like your ring finger. And so theta equals, you have a 30 degree in here, or pi over 6. So 6 pi over 6 plus another one is 7 pi over 6. And then in this quadrant, right, if you, if you think 12 pi over 6s is 2 pi, right, you go one back, it's 11 pi over 6 to get to this spot, because this little thing in here is a pi over 6. So the other one is 11 pi over 6. And that would be it. So here you're getting, 1, 2, 3, 4 solutions to that thing in the first lap on the circle. All right. So this last problem's a little different. It actually turns out there's a whole bunch of trig identities out there. And in Algebra 2, we really just show you guys two of them, two kind of sets, I should say. So we've got the Pythagorean ones, the ones like we used right here. So Pythagorean trig identities can help you do problems like this a lot easier. But that one doesn't really use identities at all. But then there's something called the double angle formulas, or double angle identities. And you can show where these come from using some other trig identities and things, and I could talk about where these come from, but there's really, it's not right now the purpose of the course. You'll talk about it some more in pre-calc. For right now, I just kind of want you guys to see how to use them. So you can kind of believe me that all these make sense. I showed where these come from. It's just out of literally x squared plus y squared equals 1, like for that one. And then, you can divide by cosine to get this one. And then you can divide this by sine squared, and you can get this one. So those ones are pretty easy to see. But basically, to see where these come from just takes a little more work that I don't really want to get into in this video. So these are all other ones that are out there. Cosine actually has 3 options, which is kind of weird. Sine of 2 theta is actually just equal to 2 sine theta cosine theta. That's it. But cosine 2 theta has these 3 things that are equivalent. And these are just called double angle because you're literally doubling the angle. If you think about it in a picture, if this is theta, right, then let's say 1, 2, maybe that is 2 theta, right? So we're literally just doing, it's like if you're doing cosine of 2 theta, there's still some sort of triangle, and you're still going to do it like cosine of the original theta is adjacent over hypotenuse. Cosine of 2 theta is, adjacent over hypotenuse, but it's going to be a different triangle. So, so you're just doing normal cosine, but you're just doubling the angle. And it turns out that there's reduction kind of formulas for what those are, and these are them. And you won't have to memorize these. I will give you these when you need them. And that's the same if you go on and take like calculus and things like that where you use them all the time. You get formula sheets and whatnot on like AP exams and things where you can use this. So, so when you need it in a problem, you basically have it. So I just want to show you kind of how we can use this and solve an equation like that. So what you kind of want to do is think about how can you reduce cosine 2 theta in this, and you have 3 options. You got these 3, and you just want to kind of think about which one of these would be helpful. And hopefully it's not too hard to see that basically the best one would really be this one at the bottom, because it's kind of like we did a problem in the last video where actually this one even, we have had these like quadratic trig equations where you can do u sub and whatnot. Here I have like sine squared and a sine. And if I did this bottom identity and I wrote this as this, then now I would get a cosine squared in here, and I have a cosine, so I can get like a quadratic cosine equation, basically. So what I'm going to do is I'm going to replace cosine through theta with 2 cosine squared theta minus 1. And then I have the rest of this stuff still left over. All right? Put everything on one side. 2 cosine squared theta, minus cosine theta minus 1 equals 0. And then you can just do u sub stuff. You can do u equal cos theta. So then, if you do that u sub there, you're going to have 2u squared minus u minus 1. That factor is actually really nice. You're going to have 2u plus 1, and then u minus 1. And so u is equal to negative a half, or u is equal to 1. Right? And then you can just go and undo your u's, right? Cosine theta then equals negative a half. So this one. And for that one, if we're asked to just solve all, solve that equation, there's no restrictions on like what quadrant we're in or anything like that. We really have to think of all ways to get negative a half, right? And so the all students take calc thing. It's equal negative, so it's not in those two quadrants, right? It has to be here, has to be here. Finger trick stuff. Basically, you want, for cosine, right, square root of fingers above over 2. And so the only way to get one finger above is basically if you're working with like a 60 reference angle in here and here. So let's just do this one in degrees. We've done radians in the other problem. So if this is 60 in here, this is 120. And then if you go 180 plus another 60, right, that's going to be 240, right? 240. And so actually I should give myself a little room, because we also can keep, instead of just hitting that, we can go around and hit it again, and around and hit it again. We go reverse, all that sort of stuff. So we really do need to add this 360n thing. So that's going to be one answer. And then the other answer is the 240 plus the 360n, okay? But that is only half of it, right? We have this other u equals 1 thing. And so then we want to think, okay, when does cosine of theta equal 1? Let's draw a little triangle or circle. The way I would think about this one is cosine is the x value as you move around the circle. So you only have an x value of 1 over here, right? And so you have to have an angle of like something equivalent to like a 0. But you could also have, 360n again from there. So you could have like angle of 0, or go around and hit it 360, or go backwards and minus 360, minus 720, whatever, right? So this one is, just another example of these kind of trig equations you run into. As you, go further in math, you'll start to see a lot more of stuff like this. And, this one is also a little trickier because you have to use these other trig identities. And it's probably about as tricky as they get, because for cosine, you have 3 choices of which one of these to pick. And you have to realize that the best one to pick is this one, because then you can do the trig quadratic kind of stuff that we've done here and here. If this had been, sine 2 theta, like you would only ever plug in that. That would be the only thing that's helpful there. If it's cosine, you have to think about it. But if it's if it's sine or tangent, these are the only 2 for those ones. Okay, and again, you will be given this, so you don't have to memorize these.